Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and we're only about 6 or 7 videos in this list, and we're still in the simple versus simple hypothesis testing mode. And here we're going to look at a Bayesian test for a simple versus simple hypothesis test. Now let's let our data, our random sample, be from some distribution, x given theta, where theta lives in the parameter space omega, and it has 2 points, theta 0 and theta 1. And it has prior probabilities of P0 and P1. So that's the probability distribution on theta. You know, they do add to 1. And we wish to test is the null hypothesis that theta is theta 0 versus the alternative hypothesis that theta is equal to theta 1. Now, let's let delta and it's a function of x, be a decision function. Now, in the previous videos, we had what's called a test function, and we called it phi of our data, phi of x. But here, since we're, it's really the same test function in the frequentist paradigm. So it's exactly the phi of theta, but since we're in Bayesian mode, we're going to call it delta of theta, and it's a decision function. And so it has the same form, so delta of x is 1 or 0, and it's a 1 if x is in this critical region, and it's a 0 if it's not in the critical region. C is the critical region. C union C complement makes up the entire sample space, and they're disjoint sets. Now, for shorthand notation, we'll let delta 0 be the case that delta is 0, and delta 1 is going to be the case that delta is equal to 1. Now note that delta is a non-random decision function in this video. We're going to let the loss function, we're going to let L be non-negative, be a loss function. And it can take on 3 values. So it's L of theta and given delta. So if we make a correct decision that the parameter is theta 0 and we indicate it's theta 0, or if it's theta 1 and we indicate it's theta 1, there's no loss. And if the true state of nature is theta 0 and we indicate that it probably should be theta 1, that we're going to have a loss of L1. Now the subscript tells you what the true state of nature is, but we make a wrong decision, right? So the 0 here, L0, means that the true state of nature is theta 0, but we made a wrong decision, and that's the loss, L0. L1 is similarly defined. L1 means the true state of nature is theta 0, but our test function says that we should accept theta 0. Now the risk function is the mean loss, or the average loss, right? So how do we take an average of a discrete variable here? There's only 3 possibilities. So it's the value times the probability of observing that, for each case. Now 0 times anything is 0, so we'll just leave it out. And then L1, which is here, times the probability of observing that, plus L0, if I said L1. L1 times the probability of observing that, which is this. Then we can write these in conditional probabilities. And then this we were calling P0. And this is an error, right? What's the probability that we reject the null, given that it's true? That is, we're going to call that alpha. Now, we don't call it a type 1 error in the Bayesian setting. That's a frequentist nomenclature. Here, it's just an error, but we're going to call it alpha. And so L1, P1, and then we're going to call this beta. And this is an error. It's the probability of making a wrong decision is beta. So probability that we conclude the null hypothesis true, but given that the alternative was really true. Now, the whole concept of a Bayesian decision function is the one that minimizes this average risk, or the mean risk, right? So the goal is to find this set C among all other critical regions that it minimizes the average loss. Now, here's a big note though. I think in our second video, we looked at minimizing a linear combination of the type 1 and type 2 errors. And notice that this is a linear combination of errors, and we want to minimize it. So that video is going to be very important in this next theorem. So here, the theorem, under the conditions on page 1, and so I guess I'm a little bit lazy. I'm not going to restate this, but this is the situation that we're in. The Bayesian decision function is given by this. So it's delta is 1 or 0, and it's a 1 if this is the case. So L0, P0, F0 is less than L1, P1, F1, and it's 0 otherwise. Now, we can simplify this if we divide both sides by F0 and divide both sides by L1, P1, we get this right here. Now the ratio F1 divided by F0, it's the likelihood ratio, but in the Bayesian setting or paradigm, it's often called the Bayes factor. And so we'll bring that in, not this video, but a later video. So this is it. So this is the Bayesian decision function. And the proof is actually quite simple after you've watched that previous video. So note that the mean loss, or the risk, is a linear combination of these two errors, the probabilities of these two errors. Now see the theorem in video Hypothesis Test, minimizing a linear combination of the type 1 type 2 errors. And from this theorem, the result follows instantly. And we're done. Now let's do a quick example. Let's let x be a continuous random variable from 0 to 1. And it's either f of 0 equal to 1 or f of 1 equal to 4x cubed. Now the prior probabilities of P0 is 2/3 and P1 is 1/3. Now the graph looks like this. So this is F0 and this would be F1. Now our loss is L0 is 1. So if the true distribution is F0 but we choose F1, we have a loss of 1. L1 is 4, and it's 0 if we make a correct decision. Now, with a sample size of 1, find the Bayesian decision function for this test. So the null hypothesis is that f is equal to F0 versus the alternative that f is equal to F1. So the decision function, based upon the theorem up here, this is L0, P0, L1, P1 divided by the likelihood ratio, or the Bayes factor, which is 4/3. Now, I want to hit that, calculates to 1/2, and of course the 4/3 comes down. Now, we can divide both sides by 4 and then take the cube root of both sides, and then we get this. So the decision function, let me rephrase that, the Bayesian decision function that minimizes the risk is if x is greater than 1/2, we choose the alternative hypothesis. If x is less than 1/2, we choose the null hypothesis. And that's the Bayesian decision function for this example. Well, that's all I have. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.